All right, so continuing with our 6.1 fun identity proofs and verifications and simplifications. All right, so taking a look, just to kind of remind you of what we talked about last time, that verification is a much lower threshold than what a proof is. That verification is you're looking at a graph, it looks like it's going to work, or it looks like they're equal. You may do a couple of cases to say that it appears that they're equal. Even over here, when I was doing this based on right triangles, that's actually not a formal proof because that's only one case. It's not representative of all cases because this is only looking at when x is acute, and obviously x, the angle, can be many more things other than acute. So proving that it works for one case does not prove that it works for all cases, and that's the big idea that we want when we do informal proof, that it has to be all cases. And so the idea is to make sure that you're using variables rather than specific values, that it's in general. You're using identities that you already know to be true to help you out, or given facts that we've already proven. So looking down here, this is the big idea that I'm trying to get across here is that no amount of verification constitutes a proof. It can give you evidence that it's possibly true, that it looks like it's true when you look at the graph, that it works in a couple of cases that you've tried, but that does not mean that it works in all cases. And so that's kind of going to be the difference between looking at what we do with verifications and what we do with proofs, if we're asking for something along those lines. Now, like for example, here in 4, I can certainly be like, hey, tangent of x equals cotangent of pi over 2 minus x. I can verify that that is equal for these two situations. You can basically take the tangent, let's do it for pi over 6. So if I let x equal pi over 6, tangent of pi over 6, okay, if we can remember from our unit circle, tangent of pi over 6, my weird way of remembering it is 6 has 2 3's in it, so this is square root of 3 over 3. And, notice I'm doing an and, I'm going to do the other side separately. Cotangent of pi over 2 minus pi over 6 is going to equal, now we might need a common denominator there just to show you all the work. This would be 3 pi over 6 minus pi over 6, which is cotangent of 2 pi over 6, or pi over 3. And cotangent of pi over 3 from the unit circle is also square root of 3 over 3. Therefore, for x equal to pi over 6, tangent of x equals cotangent of pi over 2 minus x. Notice this does not mean, let's call that A. That does not mean that it works in all cases. It means it works in that one case. That's great. It gives us some evidence that it may be true for all, but does not prove that it's true for all. We could let x equal, the other one, 7 pi over 4. We'll do the same thing, tangent of 7 pi over 4. 7 pi over 4 is in quadrant 4, where tangent is negative, and the pi over 4 family, it's 1, so negative 1. And, okay, we do the other side, cotangent, pi over 2 minus 7 pi over 4. That would get a common denominator, cotangent of 2 pi over 4 minus 7 pi over 4 equals, I'm going to come down because I'm running out of room, cotangent of negative 5 pi over 4. Negative 5 pi over 4 is in quadrant 2, where cotangent is negative, and cotangent reciprocal of tangent is still going to be negative 1 as well. So therefore, for x equal to 7 pi over 4, tangent of x equals cotangent of pi over 2 minus x. But hopefully you see the difference in this problem and some of the ones that we did, the formal proofs that we did earlier. The formal proofs that we did earlier with the transitivity and the transitive property shows that it works for all. This just shows that it works for two angles. And it could work for a million angles and still not be true for all because there may be one case it doesn't work for. Now, the one thing that plugging numbers in, though, why we do that is we do an investigation to ourselves about whether or not something is going to work out and be true and be an identity, is that looking at the graph, plugging numbers in, trying a couple of cases. This is all investigations that mathematicians will do to try to determine whether or not something may be an identity. And then once we feel like we have conviction, strong conviction, the more that we do, the more conviction we have that it is an identity, we will then start looking for a formal way to actually prove it. Now, I will tell you the advantage, though, to plugging numbers in. And that advantage, and I'm going to highlight it down here because that's an important advantage. While you can't prove it's true for all by plugging numbers in, you can certainly prove that it is not true for all by basically showing that it doesn't work for something. So it only takes one counterexample. And so that's why we do this whole plug and chug thing, that if I'm plugging in and I find one that doesn't work, then clearly it's not an identity. So, for example, down here at the bottom, and you guys love 5a. This is the one where you guys are always telling me that the square root distributes over a addition, which it doesn't. So as much as you guys back in Algebra 2 kept distributing that square root over addition, all I need to prove to you that this does not work in every case is to show you a counterexample. So my counterexample, I'm going to let x equal 3 and y equal 5, just as an example. And then I'm going to show you. All right, so that would be the square root of 9 plus 25, which is going to equal square root of 36, or 6. But, notice my word here, I'm not saying and, I'm saying but. If I do 3 plus 5, that equals 8. Clearly, 8 does not equal 6, so the square root of x squared plus y squared does not equal x plus y in all cases. We found an example where it doesn't work. Even if it works in a couple of cases, it's not an identity. You can't distribute your square root over the addition. Same thing is true here. This is another common mistake that we see with trig functions. You want to distribute the sine function over two angles. You want to say that the sine of x plus y inside, you guys want to think that it distributes. And it does not. Distribution is very rare for functions. And so just to show you that it doesn't work, let's pick some values. And you may have different values. There are plenty that don't work. And don't think that just because you find one that does work, that doesn't mean that it's true for all. Remember, that's the whole investigation where you plug and chug a few values in. The more you get that work, the more convinced you are, but you can't prove it. But hopefully as you're plugging and chugging, you may stumble across some that works. I'm going to let x equal, let's do pi over 6, and let's let y equal 5 pi over 6. I'm mostly because I just want a common denominator. I like it to be nice. So that would make sine of pi over 6 plus 5 pi over 6 equal to the sine of 6 pi over 6, or pi. And if you will recall from the unit circle, your unit circle terminal point over here is negative 1, 0. Sine is the y-coordinate, so that would be 0. But if I was going to do the other side, sine of pi over 6 plus sine of 5 pi over 6. All right, sine of pi over 6, if you remember, that's your 30-degree angle. That's your 1/2. And sine of 5 pi over 6 is in the same family. So there was pi over 6 with a y-coordinate of 1/2. It's in the same family, so it also has a y-coordinate of 1/2. And this is equal to 1. Clearly, 0 does not equal 1. So the sine of x plus y does not equal the sine of x plus the sine of y in all cases. Now, that's not to say that it doesn't sometimes work. Remember, this isn't saying that it never works. It just says that it doesn't work for all cases, so it's not an identity. So if it's not an identity, you cannot use it to substitute when you're simplifying or solving. All right, same thing over here. You guys get so gung-ho on the Pythagorean identities, and those Pythagorean identities, cosine x plus sine x equals 1. Oops, no, wait a minute. It's supposed to be cosine squared x plus sine squared x is the equal to 1 is the known identity. I'm going to let x equal pi, and let's let, that's all I need. I don't need a 1. So let's just let x equal pi. Let's test it out. Let's see what we have. All right, so cosine of pi plus sine of pi. Cosine of pi is the -1. Sine of pi is the 0, so that's equal to -1. But 0 does not equal -1. We'll say but clearly, because I don't have to do the other side because it was a constant. Oops. Let's erase that, and let's really write what I mean. But clearly, -1 does not equal 1. So cosine of x plus sine of x does not equal 1 in all cases. So we have disproven that these are identities. These are not identities because they're not true for all in their domain. All right, so basically what I would like to do, I'm going to pick and choose a couple of these to do. You've got some videos to watch with some extra examples. I'm going to do a couple, and then I'm going to let you guys do a couple, just to kind of show you how it works. So here we're simplifying. I'm going to take this really complicated one. Let's do C. And I'm going to come down because we don't have a lot of room. So the first thing I'm going to do is I may start looking at things and trying to see kind of how we can relate them. Notice that right here I have a secant of negative theta. Every single time you have a secant of negative theta, you definitely want to go ahead and take that out, because that's really something that we just don't want to leave in when we are doing problems. I'm going to do some substitutions here, and I'm going to do more than one, but that's legal because we're going to be able to clearly match up where things are. This 1 over cosine is the 1 over cosine. That's the reciprocal of secant. So let's make that secant theta minus 1. Let's see how that's going to work for me. Then over here, I'm going to leave the cosine squared theta. I'm going to change that secant of negative theta, and we will remember that secant's one of the even ones. And an even function, the secant of negative theta and secant of theta are the same. So I'm making that substitution there. And then just to keep my colors going, oops, let's do pink. I took this out right here and replaced it with that. So you can see I'm kind of lining it up. All right, let's go over here. Now, 1 over cosecant squared theta. Remember that that's a reciprocal because it's in the 1 over. So we're going to replace that with, sine squared theta. Sine squared theta. All right, so we look at that, we're like, okay, that's great. We've kind of made our substitutions. And so here, just kind of keeping it in line so that color code a little bit, those are my 3 substitutions I made. So the only thing I did was a substitution. Now, I'm going to look at it, and hopefully you'll recognize that you've got a cosine squared plus a sine squared. Oh, that's the Pythagorean identity. So we're going to bring down everything else, and we're going to do one thing. That substitution is going to become secant of theta plus 1. And that should be an obvious thing when people are looking at it, because if the secant of theta is still there, here and here, they're going to be like, oh, what happened? That cosine squared plus sine squared turned into a 1. Oh, yeah, that's Pythagorean identity. Now, when I get to here, I'm going to be like, oh, wait a minute. That vaguely looks like the difference of perfect squares. Like if I were to multiply that out, sometimes we're going to do a little algebra, that's secant squared minus 1. Okay. Now maybe we're going to scroll back here really fast to, I believe somewhere we did a whole bunch of these Pythagorean identities. And let's see, secant squared minus 1. Right there is my secant squared minus 1. That's equal to tangent squared. So let's come back down here. I can make that substitution. And so my final answer in simplifying is it's tangent squared theta. So ding, there it is. Notice that as we went through, that what you're doing is you're looking at this and making substitutions. I did a little algebra. I noticed another Pythagorean identity, made my substitution. See my transitive format, that looking at that, you have your clear, what the side you started with your expression, your equals, your equals, your equals, and your equals. So our conclusion is that the first equals the last. All right, finish up these for homework and